Welcome to Data Science 1, probability distributions. Okay, so the last video we talked to the idea about this thing called a random variable. Okay, a random variable basically is how we turn what we see in our experiment into a number. So it's the scale at which you measure the outcome. So formally it's a function that goes from S to the real line, but I always think of it as how did I measure the outcome? Okay. They don't need to be unique. You can measure different outcomes in many different ways, as we looked at the last video with the fish, right? You can measure its weight, the length, whatever. It's random since we don't know the measurement before the experiment. Okay, so a probability density mass function, f, is a function that goes from r to 0, 1, such that the probability of an event, E in S, is the same as the probability that the random variable matches that. Okay, that's essentially what these things mean. So basically f of x needs to match the probability of the event that was mapped to x. And I know at this point the idea seems a bit difficult, but it really isn't. It's just you got to think about things. And if you're willing to think about things, it's not really difficult. So we'll look at a few examples and hopefully we can understand the concept here. So we're going to go back to our dice. So if we're looking at simple, fair, six-sided die, then the sample space is this. Okay? Let x be the random variable that corresponds to the number of dots on the up-facing side. Okay? So this is how we're measuring a side. We're saying that it's the number of dots. So like here we have 1 dot. Here we have 2 dots. 3 dots, 4 dots, 5 dots, 6 dots, and you notice our random variable is 1, 2, 3, 4, 5, 6. Super easy. Okay, so if I trace this backwards, f of 1, which is probability mass function or density, or not density, but distribution, plug in 1, well, I need to go back and look at, this got to match the probability that x equals 1, so I have to look back into the sample space to see where that occurs. And that occurs with this particular outcome, and we know from before the probability is 1/6. Okay, now let's go a little more complicated with 2 dice. Okay, well, and I can do each one of these all the way down to the entire probability distribution, right? We just go back and look backwards and things work out. Now let's go to 2 dice. Okay, if you remember, this is all the possible outcomes. There's 36 of them. But the random variable that is the sum of all the up-facing dots only has 11 outcomes, okay? And you'll see why here in just a second. But we just need to think about how to do this. And remember, the whole reason we're thinking about these things is so we don't actually have to conduct the experiment. Okay. So things get more complicated when we're playing with 2 dice, but that's okay. Since each roll has 2 faces facing up, we have to record the 2 faces at a time when we add them together. So the probability, or f of 1, is equal to 0, since there are no outcomes that have 1 as the total of the up-facing dots, right? You have 2 dice, so the lowest you could get is a 2. Okay, and if we did get 2, f of 2 is equal to the probability that the random variable is 2, which is this particular outcome, and that's 1/36. Okay, that's the only outcome that is equal to 2. However, if I go to 3, f of 3 is the probability that x equals 3, and there are 2 outcomes in here that have that particular feature. Okay, and that would mean our probability of getting a 3 is 2/36. Same thing, go to 4, 3, 1 and 3, 3 and 1, and 2 and 2. So there are 3 outcomes in here out of the 36. So the probability x equals 4, or f of 4, is 3/36. And you can keep playing this game as you go along, and you add things up, and you get 4/36, and so on. Now, if you keep doing this, you'll end up with what's called a probability distribution. It has all of the values of x listed and a probability associated with each. And I put this in a table because there's no point in keep looking at all those dice over and over and over again. But this is what you end up with. 2 is 1/36, 3 is 2/36, 4 is 3/36, 5 is 4/36, 6 is 5/36, 7 is 6/36, and then you work your way back down. Okay, and this is the simple idea and these are the probabilities associated with it. And this is basically, here's the value of the x, and here's the probability of it. Now, it turns out that in many of these cases, we will be able to define x and actually have a nice formula for f of x. All right, so this also has some properties. For discrete or countable outcome experiments, like dice, then f has the following property. Number one, it's a probability. So it has to be greater than or equal to 0 for every value of x we put in there. Okay, remember x comes from, little x comes from the real line. Okay, and if I sum up all the x's on the real line plugged into f of x, I'm going to equal 1. Okay, so this, for continuous uncountable outcome experiments, we have the similar properties, but here we're going to have that this density, it'll be a density at that point, has to be greater than or equal to 0 for all of the x values that are in the real line. And the integral over this will be equal to 1 because there's a subtle difference here once we go to continuous, but it's really not that difficult, so don't panic over it. And that's where we're going to start off next time, is we're going to start looking at specific types of experiments and the probability distributions and random variables that go with them. And we'll do that for the next several videos so you get an idea of how probability is put together, and it uses all of the ideas we've talked about so far. These ideas are the keys to putting everything else together. And once we get far enough, we'll put some other pieces in there, and we'll really be able to say lots of things about probabilities and about events. But those are for later videos, so I'll see you in the next video.